Hi, today we are going to continue with this indicator, more precisely the miles indication here. If you didn't see the first episode, you can click somewhere here. The DME miles works with an ARINC 561 6 lines interface. So we have some details on that manual for the Collins 331A. Okay, so we can see these three pair of lines here. There is a digital synchronization line, a digital clock line, and a digital data line. We can see here some details regarding this interface. There is first an 11 kHz clock signal. Okay, so we have 32 bits of data here. So the first byte corresponds to the label. Bits number 1 and 8 are at high level, so this corresponds to the label 201 in octals. The second byte is at low level, so it is called register clear. We have here 4 BCD datas for the display, but we can see that the LSB is here, MSB here. Regarding the transmission, we need to permute all bits. There is an example here for 238.6 miles. We have here 6 for tenths, 8, 3, and 2 here. Okay, it is close to an SPI bus. There is a difference regarding the synchronization line. We can see that this signal is at low level during the low level of the clock input here. For the test, I will use this Curiosity development board for microchip. So this is a nice development board. It is not expensive. Okay, so there is a potentiometer, 2 push buttons, 2 LEDs here. I have built this display board, which permits to display some informations. For the ARINC 561 interface, I have used an SPI of the microcontroller, a 32 bits configuration. Okay, you can see on the screen the configuration of the SPI bus. For the synchronization line, an external interrupt is used. So interrupt 0 input here is connected to the clock of the SPI, and there is a simple counter. You can see that at the clock number 8, the synchronization line is set to 0, and 1 clock after, the synchronization line is set to 1. We have seen that we need to permute all 16 bits of the data. This is done using a union. A union is something which is very interesting in some particular cases. Okay, we can see here there is a union between 16 bits value corresponding to the data, and we can see here a bit field structure with 4 BCD datas. Okay, so we need actually to permute all bits. So this is done first by the permutation of the BCD datas themselves using the union here. And there is another bit permutation which is done by this table here, BCD swap. So first I have used an sprintf function which permits to convert the 16 bits value into a string. And after that I have applied the table which permits to permute all bits of each BCD data here. At the end, the 16 bits value here is fed to the low word of the SPI bus here. Okay, the high word is 8100. It corresponds to the label 81, followed by 00 here. Okay, we can see that the code is quite short, but be careful because this kind of thing is not portable because it depends on the endianness of the compiler. For the first test, I have connected this ARINC 561 generator to the input of this indicator. So we can see on the scope here the signals of the ARINC 561 bus. We have here the synchronization line. So we can see here the low level for bit number 8. The second signal here shows the datas. The first byte corresponds to the label 81 in hexa or 201 in octal. We have here 4 BCD codings, and here we have 32 pulses for the clock signal. You can see that there is a small lamp here for the decimal dot. There is a specific feature in case of a dead lamp here. In that case, the indication here can be misleading. So for that, there is a detection of the current flowing through the lamp here. So it uses this NPN transistor here and this shunt resistor. So of course, I will not disconnect this lamp. It is complicated. It is possible to provide a short circuit between the grid here and the ground. Okay, so I have connected this test clip to the grid of the transistor. So I will connect this signal to the ground. We can see that this digit alternates between the figure and a minus sign here. The second test will be a little bit more complicated. Okay, I will connect this DME test set to this board. This board will extract the synchronized dual pulse and the value will be displayed on this indicator. For the synchronized pulse extraction, the idea is to do an averaging of different acquisitions. Acquisition is done every 1.236 microseconds in order to have a resolution of 0.1 mile. It is difficult to write a code in C. This is why I wrote the acquisition routine in assembly language directly. First, we can notice that this value is close to 1.25 microseconds. Therefore, the internal clock frequency of 8 MHz is used, and fortunately it is possible to adjust the clock frequency inside a range of plus or minus 1.5%. So this is why the clock frequency is adjusted at 8.09 MHz. So therefore, one CPU cycle is exactly 1.1236 microseconds. That is to say exactly 0.01 mile. So we can see the loop here for the acquisition. The duration of one loop here is exactly 1.23 microseconds. There are here 10 CPU cycles exactly. It is also necessary to have a linear code. The idea here is to use the carry bit C. These two instructions permit to copy the input pulse bit on RB8 to the carry bit C. And the main instruction is this one. So this is a powerful instruction. This is an addition with carry bit. The first register here is null. W1 is actually a pointer. So this permits to add the content of the pointer to 0 plus the carry. It is what we want. And the result is stored on the same pointer but with a post-incrementation. This permits to add the carry bit to the value which is at address W1 and W1 is incremented. After that, this function permits to extract the time between the synchronization and the beginning of the first pulse. Okay, so this is done by this loop here. If two pulses are detected, there is here a measurement of the time between the two pulses. The time should be 12 or 30 microseconds. Okay, so if we have two pulses and if these two pulses are separated by 12 or 20 microseconds, actually the value of the first pulse is returned, which corresponds to the distance with resolution of 0.1 mile. Otherwise, an error is returned. We have here the acquisition function. So first, the array is cleared. After that, there is a loop for several acquisitions. The number is set to 7. After that, I wrote a DME test function. This function permits to show the content of the table on an oscilloscope. For that purpose, I built a simple 3-bit DAC on the board Okay, we can see this test function here. So there is a synchronization line, and after the complete table is read, and the 3 LSB bits are fed to the DAC. So this permits to see the averaging of the dual pulse. So we can see on the scope the averaging of the pulses. So we can see that the synchronized pulses have an amplitude higher than the random pulses. The amplitude of the random pulses is 1, sometimes 2,